All right, let's look at this situation. It's kind of a cool one. Um, so what we have here is we have this wedge. So the wedge-shaped kind of object, you can consider it to be made of wood or something. I don't know, kind of picture it in your mind, that helps. But it's sitting on a horizontal surface, and this is important. The interface between the wedge and the surface that it's sitting on, that's a frictionless interface. So that's kind of counterintuitive, but we got to take that in. So no friction at the interface between the wedge and the substrate that it's sitting on, which is a horizontal surface there. Now, on top of the wedge, what we do is we release a solid sphere from the top of it from a rest, and the solid sphere rolls down the wedge. Yeah, so it'll be accelerating down the wedge. And the question here is to determine the linear acceleration of the sphere and the acceleration of the wedge. So we're interested in how both these bodies are moving. Hmm. You might ask yourself, well, what would happen here? Now this one's, it's hard to like build this in your house because it's hard to come up with a frictionless surface. You can maybe do something that is approximating this, but this one's going to be harder to build. So you might have to just hold this one in your mind. So the sphere is going to rotate down the wedge. Let the whole system's at rest, right? And then you let it go. The sphere is going to roll down the wedge. So if I'm going to draw in the acceleration of the sphere, right, I might say, all right, I know the sphere is going to be accelerating in that direction because I know it's just going to roll down the wedge. So it'll have, it'll rotate and it'll translate since it's rolling. So what's the wedge going to do? Maybe you're not sure, like, I don't know what this wedge is going to do. Maybe you've got some idea of what it's going to do. But I'm going to start just by choosing something where, like, say I'm not going to put any, I didn't really think about, I wasn't thinking about conservation of momentum, which would be a good thing to think about right here, right? I wasn't thinking about any of that stuff. So I just said, well, I don't know what the wedge is going to do. I don't know. I'm just going to pick a direction and I'm going to pick it. I'll say, here's acceleration of the wedge. It goes that way. Okay. So whether that's right or not, I don't know, but we need to kind of proceed with the problem anyway, right? So let's do so. We'll start, of course, as we do with free body diagrams. So we'll start with the free body diagram um, for the wedge. These are cool free body diagrams to do. This good ways to test your skill. Free body diagram for the sphere, since it's translating. And then we also need a torque diagram for the sphere, since it's also rotating. So again, we just look at all of the bodies in the problem, figure out what needs free body diagrams, if anything's translating, if anything's rotating, it needs a torque diagram, and we use those diagrams to generate our equations. So if I look at the wedge, now this is cool. Think about it. This wedge, if I'm going to draw the free body diagram for the wedge, I do not need to rotate this coordinate system. In fact, I don't want to rotate this coordinate system, right? Because the acceleration of the wedge is going to be parallel to the substrate it's sitting on. So the acceleration of the wedge is going to be horizontal. The wedge is not going to have any vertical component to its acceleration, right? It's not going to be jumping up off that surface or doing anything like that. So I'm not going to rotate the coordinate system for the wedge. Remember, our motivation for rotating the coordinate system is to keep the acceleration on axis. That's it. There's no other motivation. So if I'm going to start by looking at the wedge, let me think about what forces are acting on it. Again, this is a non-rotated coordinate system here. So I have normal force on the wedge, upward. I'll just call that N. That's due to the surface beneath it that's supporting it. Remember that surfaces can exert normal forces and frictional forces. There's no frictional force at the surface underneath the wedge, but there is a normal force there. I know that I have the weight of the wedge. Mass is given as 3m. Okay, now the place that I need to focus my attention is where the wedge is in contact with the sphere. So I'm just going to kind of circle where that happens on the physical diagram. So that's where I'm looking at, right? So when I'm identifying forces, I have to look at what's in contact with the body. So it's in contact with the sphere right at that point. That means the sphere can be exerting force on the wedge, and in fact is. So you'd want to ask yourself then, okay, what forces? So first of all, a normal force, right? There's a normal force at that interface. We've done tons of normal force stuff, stacked objects, etc. So you want to bring that knowledge in here. That normal force is not going to be straight down though. Remember, it's normal to the surface. So it's downward on the wedge, but normal to the surface. So for that, I will think about a rotated coordinate system for the sphere itself, and that might help me to sort of picture the direction of that. So this normal force, it will be something like this. Okay, here's my angle phi, and I'm going to call this n prime, the normal force at the interface between the sphere and the wedge. Okay, great, there's a normal force there. And then that surface at that interface, there must be a frictional force. There has to be a static frictional force because I'm told that this sphere exhibits perfect rolling. Perfect rolling is going to happen when you have a static frictional force, right? That's what allows it to happen, such that at the contact patch, there is no relative motion between the two materials, right? The two materials are at rest with respect to one another at the contact patch. So what might be helpful here is to think about what does the direction of static friction have to be on the sphere, and then know that you're choosing the opposite direction because it's going to be a third law pair on the wedge. And with that, we've done that a bunch of times now. Hopefully that's getting a little bit more comfortable. And we also know that it's going to be 90 degrees from this normal force, right? Frictional forces are um, frictional forces are parallel to the surface. Normal forces are normal to the surface. Okay. So obviously I didn't draw these forces into scale, or this object would look like it was accelerating downward. That normal force we could consider to be a lot higher there. But okay, those things being said, what's most important about our free body diagram is identifying our forces correctly and getting all the angles right, because we're going to figure out the magnitudes later. So I'm going to call this just F sub s. There's only one magnitude of static friction in this problem, so I don't have to add any more notation to that. All right, let's look at the sphere now. And it might be, if you want to start with the sphere and then do the wedge, that might be helpful. I don't know. Because of my choice of acceleration for the wedge, I made kind of a random choice. Might be different from your choice, but because of the choice I made, I'm going to say positive rightward for the wedge to align with my acceleration direction. So now I'm looking at the sphere. So for the sphere, I am going to rotate my coordinate system. Again, that's to align with the direction of acceleration for the sphere, which is not the same as the direction of acceleration for the wedge, right? So this is kind of a neat problem in that way. It makes you have to think about each body, and it makes you realize how important it is to have a free body diagram for each object in this problem. So yeah, so here I'm rotating my coordinate system. I've got the weight of the sphere, and then the other forces are going to be third law pair to that n prime and f sub s. So I'm going to do those in pink, just kind of align with what those two were. So my f sub s on the sphere is going to be to the left, and normal force, again, this is a rotated coordinate system. Now, n prime. And these two, this f sub s and n prime, are the third law pair of the pink, n prime and sub s in the free body diagram for the wedge. And you might say, how are they? They're not opposite direction. They actually are opposite direction. You have to remember that in the free body diagrams, the wedge free body diagram is not rotated. The coordinate system is not rotated, whereas we have rotated the coordinate system for the sphere, motivated by the direction of acceleration. So I'll put my signs on there in the direction of acceleration. And then a torque diagram for the sphere. This is fairly simple. There's only one force that causes torque on the sphere, and that is the force of static friction. I've been using pink for that, so I'll continue. So even though there are three forces on the sphere, you can see from the sphere free body diagram, only one of those forces actually causes a torque. So there's my torque diagram. And from that torque diagram, I can generate an equation. But I'll go through and do my Newton's second law equations first, my torque equation, and then like that's it. I mean, after that, you've got some algebra to work through and a little more concept, but the bulk of your physics is done at that point. So if I look at the wedge here, I'll look at, I don't know, I can look at my horizontal first. F sub s cosine phi minus n prime sine phi. Watch your angles here. In this free body diagram, notice I have one of my angles with respect to the vertical, the others with respect to the horizontal. So you got to watch that. Equals 3m acceleration of the wedge, right? There's my x equation. I'll do my y equation. N minus n prime cosine phi minus 3mg minus fs sine phi equals 0. Okay. Got two equations generated out of that. I can get a couple equations for my sphere diagram. I'll do the same thing here. Mg sine phi minus f sub s equals ma sub s for acceleration of the sphere. Will not be the same as the wedge, so I need a notation there, right? And then n prime minus mg cosine phi is equal to 0. My vertical, that one's simpler. And then if I look at my torque diagram, I'll just put that underneath these other ones. My torque diagram is just going to give me r f sub s equals I value for the sphere a sub s over r. No one's asking me about angular acceleration, so I'm just going to go ahead and write this in terms of the translational or linear acceleration right away. I'm not even going to put an alpha on my paper right now. So this is pretty good. The I value, since this is a solid sphere, the I value is something you can look up in the table. You should be fairly handy with the shapes that are in that table, right? So for a solid sphere, we have 2/5 m, little m, right? Yeah, little m r, big R squared. So that's for a solid sphere. That's relevant. But yeah, I mean, I've got 5 equations, really 6 equations if you count that one there. So I have enough equations as I have unknowns. And the details, the rest of this, as far as solution goes, you can look up in the written solutions. The physics is fairly done at this point. Really keep a close eye on your notation here and don't confuse those two accelerations in order to get to the right final expressions there at the end.